The basic proportionality theorem, also known as Thale's theorem, named after the ancient Greek mathematician Thales of Miletus. It answers a fundamental question about triangles. What happens when you draw a line parallel to one side of a triangle? The answer is beautiful and simple. That line divides the other two sides proportionally. This is the cornerstone of similarity and scaling in geometry. Let's explore it step by step. The theorem statement. In triangle ABC, let there be a line parallel to side BC, intersecting AB at D and AC at E. Then the ratios of the divided segments are equal. Add over DB equals A over AC. This means the line cuts the two sides in exactly the same proportion. We can also express this in two other ways. Add over AB equals A over AC. And dB over AB equals AC over AC. Let's see this in action. Let's see the proportional division in action. In this triangle, D is parallel to BC. Let's measure the lengths of AD and DB on side AB. Now let's measure A and AC on side AC. Even though the numbers are different, the ratios AD to DB and A to AC are exactly equal. Watch as we compare the two fractions side by side. This works no matter where you draw the parallel line, near the top, in the middle, or close to the base. The proof of Thale's theorem using triangle areas. Here's the clever area argument. Step 1. Connect B to E and C to D to form triangles BDE and CDE. Step 2. Note that triangles AD and BDE share the same height from E to AB. So their area ratio equals AD over DB. Step 3. Similarly, triangles AD and CDE share the same height from D to AC. So their area ratio equals A over AC. Step 4. The key insight. Triangles BDE and CDE lie on the same base D and between the same parallel lines D and BC. Therefore their areas are equal. Step 5. Since the denominators are equal, the two ratios AD to DB and A to AC must be equal. This completes the proof. The converse of Thale's theorem. The theorem also works in reverse. Suppose you draw a line through triangle ABC that cuts side AB at D and side AC at E. If the ratios AD over DB and A over AC are equal, then the line D must be parallel to BC. This is incredibly useful in geometry problems. Whenever you find proportional division on the two sides, you instantly know the line is parallel to the base. The converse is just as powerful as the original theorem. Special case. The midpoint theorem. When D and E are exactly the midpoints of AB and AC, then AD equals DB and A equals AC. So AD over DB equals 1 and A over AC equals 1. The condition of Thale's theorem is clearly satisfied. So D is parallel to BC. And by similarity, D equals exactly half of BC. This is a beautiful special case of the general theorem. In fact, the midpoint theorem is just Thale's theorem with the parallel line drawn exactly halfway up a triangle. Summary of the basic proportionality theorem. The main result. In triangle ABC, if D is parallel to BC, then AD over DB equals A over AC. The converse. If AD over DB equals A over AC, then D is parallel to BC. The proof uses a beautiful area argument. Triangles sharing heights and equal areas between parallel lines. And the midpoint theorem is a special case where the ratios equal 1. Thale's theorem is truly a cornerstone of geometry, essential for similarity, scaling, and countless geometric proofs.